All right, 2C.10, inverse of an exponential function is the log function, okay? Before we were talking about log expressions, which is what 2C.9 is over, is log expressions, right? Manipulating, practicing that, and that's what your quick check was going over. Now we're going to dive into the function itself. So just like when with previous functions, we can also graph log functions, which you learn how to do in Algebra 2, okay? So this should be like, oh yeah, I've done this before. I've graphed this function before. When you're graphing a log function, you're paying attention to the A and the B value, okay? Your B has to be greater than 0, meaning that it has to be positive. So B has to be positive. It cannot equal 1, and A cannot equal 0, which makes sense because if I make A equal to 0, then the entire thing is equal to 0, okay? Because exponential functions and log functions are inverses of each other, right? We would expect the characteristics of the input and the output values to switch, correct? So you remember with exponential functions, they do this, right? Yeah. Well, our log function is the inverse of that. Remember, if I'm an inverse, it's going to be reflected. Pretend that's a very straight axis. It's going to be reflected over the y equals x line. So our log function is going to be, let's try that again. Why it won't let me draw? Okay, that's as symmetrical as it's going to get for us today. But our log function is going to be behaving opposite. Okay, exponential, you have your, so this is our exponential, and you're going to have your your horizontal asymptote. With log, you're going to have your vertical asymptote. So if you can graph an exponential function, then you can also graph a log function, correct? Yes. Okay, so when we are looking here, and we recall the exponential function over equal parts. So when you're analyzing exponential function, you know that it's exponential because your x values are equally parted. So each one is spaced apart by 2, right? Yes. Okay. Your f of x are changing by some type of multiplication, right? There's a rate of change that's taking place. So to get from 2 to 4, we multiply by 2. To get from 4 to 8, we multiply by 2. To get from 8 to 16, we multiplied by 2. This is what makes it an exponential function model. Yes? Do you remember that? When we went through linear, quadratic, and exponential, okay? Now, log is going to be the opposite of that. Log is going to be the reverse of that concept. So for log, instead of having a pattern between your multiplicative pattern between your y's, your output is now between your input, your x's. Your x's are growing in some pattern. So when you look here, my x's are the ones that are being multiplied by 2, and my y's are the ones that are equally spaced. That's how I know that this is a log function model instead of a exponential function model. Okay. And this again is because log and exponential functions are inverses. So their input and outputs are switching roles. How do we feel? Do you have questions about that concept? All right. So at your group, what I want you to do on example number 1 is to decide which tables are logs, which tables are exponential models, or which is neither. Okay. So it's either going to be a log, an exponential, or neither model between function h of x, k of x, p of x, and l of x. And go. All right. So h of x, we said is exponential. Why is it exponential? The x's are equally spaced, and your multiplication change takes place on the y, right? We're multiplying by a half, correct? All right, k of x. What is k of x? K of x is log. It's a log model. K of x is log because
the y is evenly spread out.
Perfect. The y is evenly spread out. And your x, your input is
3.
multiplying, changing with multiplication. Okay. C.
Either it's linear.
Perfect. Good job. Okay. And where we at? Oh, D, L of x. It's log. And why is it log? Because you said so. Y is equally spread out by doing what? We're at -3. We're adding -3 every time, right? And on here, we are multiplying by 2. Do you feel confident in identifying between an exponential and log table? Yeah? Doable? Cool. All right, let's keep it pushing. Okay, so now we're going to talk about inverses in general and how to verify if a log and exponential are inverse. In order to do that, just like any other inverse function, you use composition. Okay, you compose the two functions together, and you'll compose f composed of g of x and g composed of f of x, and they both need to equal x. Okay, if they both equal x, then you know that these are two inverses of each other. Okay. That's where your log and exponential properties, that quick check comes into, seeing if things cancel out because the bases are the same or the powers and the bases are the same. Okay. Two important properties of inverse functions. Okay. Graphs of inverse functions, if you're going to look at it graphically, they're going to be reflected over the y equals x line, correct? Remember that? Correct. Imaginary line through the origin. Then if the points x1 and y1 is on the graph, then if they're inverses, then you're going to also have y1, x1. Because inverse means that your input and your output values swap, right? Okay, and so therefore they have to both be present on the graph. All right, so we're going to prove first algebraically, and then we're going to look at graphically. So up first, we have example 2, and we want to show that f and g are inverses functions by proving by using composition. So f composed of g of x and g composed of f of x, okay? So we're going to show algebraically why these two are friends, okay? So first, we're going to do f composed of g of x, which means that we're taking f and we're substituting in log base 3 of x. Oh, is there? Okay. So that means where x is in f of x, it becomes log base 3 of x. So now we have 3 to the log base 3 of x. Our properties state that if the base of the log and the base of the exponential are the same, they do what? They cancel each other out, and we're left with just x. Okay, to show g f of x equals. So if I'm going to do this one, this time I'm taking the function f of x and plugging into g. F of x is 3 to the x. That means in g, where x is, it becomes 3 to the x. So we get 3 log base 3 of 3 to the x. And again, the base of the log and the base of the exponential are the same in the argument. So what do? They cancel out, and we're left with x. And this is how you prove that f of x and g of x are inverses. Okay, algebraically. If they both do not come out to equal x, then they are not inverse. How do we feel about algebraically? Questions, comments, concerns? Okay, let's talk about graphically. So if we have k of x equals 2 to the x, one of our most commonly used exponential functions, and we want to sketch the inverse of the inverse of k to the x, which is log base 2 to the x. Okay. In order to do this, we're just going to create a table, choose points, and plot them. Okay. The other thing that you can do is take the points and you're going to reflect them across the y equals x axis. So if I'm here and I need to reflect it, how am I going? Pew, pew, over it all. Does that make sense? So you can do that. You can create a table. I'm going to do a table so you can visually see it. So originally, we have k to the x. On k to the x, points that are pretty easy to use, I'm going to go with negative 1, which is at 1/2. I'm going to go with 0, which is at 1, 1, which is at 2, and I'm going to go to 2, which is at 4. Do we all see where those points came from? Okay. Now we're going to make the table for our inverse. Our table for our inverse literally means I'm doing what with these points? I'm switching them. I'm reversing. So now we're at 1/2, negative 1. We're at 1, 0. We're at 2, 1. And we're going to be at 4, 2. So I go to 1/2 and I go down to negative 1. It's going to close out for a second. Why? Just to annoy me. There we go. Okay, and then I'm going to go to 1, 0. Then I'm going to go to 2, 1. Then I'm going to go to 4, 2. And not only did that change, but also did my asymptote. So there is an horizontal asymptote. Now I have a vertical asymptote. So I'm not going to cross the y-axis. And there is my best ability of trying to get close but not cross. Okay, so this is my k of x, and this is my k. And notice that the points are reflected over the y equals x line. Questions about graphing the inverse? No? Cool. No, you wouldn't. All right, next. Here it says the exponential function h of x equals a to the x. It contains the points 2, 3, and 6, 27. Find the average rate of change of y log a to the x over the interval 3 to 27. Okay, so what happens here is that in order for us to find the average rate of change of the log, because it didn't say find average rate of change using those points, right? It says it wants us to find the average rate of change of log a to the x. And log a to the x is the inverse of a to the x. Does that make sense? Okay. So log a to the x is the inverse of a to the x. This is the inverse. Okay. Because it's the inverse, that means that my points aren't 2, 3. The points that we're actually using are 3, 2, and 27, 6. Does that make sense? Okay, so the original were 2, 3, and 6, 27. Therefore, the inverse, its points are going to be 3, 2, and 27, 6. Can I easily find A rock now? Yes, finding A rock. This is my X1, my Y1, my X2, and my Y2. So A rock equals the change in my Y over the change in my X. So that would be 6 minus 2 over 27 minus 3, which gives me 4 over 24, which equals 1 over 6. Okay, so do you see how they tied something from unit 1 to this?
Yes.
Yes. So you can, it's all there, it all comes together, but it's not hard. It's just reading, paying attention to what's given, and going from there. How do we feel about 2C.10?
Wait, so is it unit 2, chapter 10?
Section 10?
So it is unit 10.